Okay, so we are going to continue on our busy schedule today, and we are just about to start with the second pure core technology session that was planned for today's schedule. I hope that you have succeeded to a little bit to rest and to get to the Israeli sun. Actually, we tried to control the weather, but it was a little bit challenging, but at least you can realize how we feel it here usually. So on our panel, on our session, we're going to have three speakers, and I would like to invite the first one, and they will give us really interesting perspective of the cyber challenges that we see today at the core technology of the topics that we meet. And our first speaker is going to be Professor Sandeep Shukla. Professor Shukla is currently head of the Department of Computer Science and Engineering Department and the Poonen and Prabhu Gold Chair Professor at the Indian Institute of Technology, Kanpur. He is an IEEE Fellow, an ACM Distinguished Scientist, and IEEE Computer Society Distinguished Visitor, and co-director of the Interdisciplinary Center for Cybersecurity of Critical Infrastructure at Kanpur. So, Professor Shukla, the stage is yours. Please.
Thank you. I'm going to put my timer on. All right, can you hear me? All right, so let me say a little bit of history. So I was working at Virginia Tech in the US for 14 years. And then in 2015, I arrived back home in India to work at the Indian Institute of Technology. And then I started looking at the situation on the ground in India in terms of defending our critical infrastructures, power system and manufacturing system and so on. And we are actually being sold nuclear reactors by various companies in the US and various Russia and France. And we are very worried about their cybersecurity as well. Now, while doing that, we realized that there was no test bed for supervisory control and data acquisition system in India, which would actually allow us to do realistic experiments on looking at the cybersecurity of various equipments and software that goes into such systems, and they're deployed all over the places. So while doing that, so we started with a very small SCADA test bed at our lab, and then now we have been funded by the government to put together a test bed that is similar to what they have in Sandia National Lab or Idaho National Lab, where actually companies can come and actually do hardware in the loop and software in the loop testing of vulnerabilities and also test the mitigation techniques and so on. So, so number of cyber crimes in India is skyrocketing, and this is a little bit old data. Since last year, since we have become demonetized and digitized, our cybercrime rates have increased substantially. But this has been a phenomenon all over the world, and India is not immune to that. So government websites get hacked, various company websites get hacked, and so on. And then state government websites get replaced by something with various kinds of messages. Now, as I understand from the news, and I haven't gotten any kind of confirmation from here, is that in 2016, December or so, or January last year, Israel power grid also was hacked, but it was not the actual power grid, so there was no blackout. Ukraine suffered this massively first here in 2015 December, in the middle of the winter, black energy malware. But next year, this year, actually beginning of this year, they got hacked again, and this time it was actually ransomware that encrypted their firmware. And fortunately, they learned from the lessons from the last year, so they had very good backup. And so it was only an hour of blackout that they had to suffer. They could very quickly flush all the devices and reinstall and so on. Television networks get hacked. German steel plant 2014 December got hacked and equipments got damaged. Turkish banks were under cyber attack last year with a massive DDoS attack, which basically can have big impact on the economy. Austrian hotel got hacked by IoT ransomware, and many of you have heard about this story, that people got locked out from their rooms and they had to actually pay ransom to actually get guests in or out of the rooms. So then we had this Dyn attack last year, October, the IoT-based DDoS attack, which is quite scary. And then since we are all so dependent on mobile devices nowadays, so mobile security issues, so we are seeing the exponential rise month to month on malware, mobile malware, and so on. So that's the global situation, and the Indian situation is that actually what we say is that 100% of the companies got hacked, but only the enlightened ones actually know that they have been hacked. But according to this survey from last to last year, 72% of the financial companies got hacked, and if you look at the oil and gas and utility industry, 37% says they have been hacked, but that seems pretty small. So our contention is that we'll be hacked. We are already hacked most of the time. We have put honeypots in our institute, and we see about 300,000 attacks per day. So and we are not critical infrastructure. So the question is, how do you design resilient cyber physical systems which are ready for detecting attacks as soon as possible and island various components, so a containment of the attack, as well as islanding and isolation of the parts that have been attacked. That is sort of the goal that we are progressing with. And in order to do this, we need a realistic system. So in the past, we have done virtual SCADA test beds, where everything was virtual except for the front end. We actually took front end from a standard SCADA vendor, and we simulated a power system using standard power system simulator and so on. But it doesn't allow us to do various kinds of attacks that we have now done on the SCADA system that we have built so far. So our approach has been that we have people working in our university who are working in machine learning, people working in program analysis, people working in our computer architecture, memory systems, and people working in formal methods, people working in robotics and so on. So and cryptography, and so we wanted to bring all of them together under the umbrella of this center. And so we proposed this center, and the way we look at it, so this is not very visible here, so we basically layered these systems. So these are critical infrastructure. What we call is an very extra large cyber physical system, right? So in this you have the the physical dynamics of the system that has to be looked at for anomaly, because many times the attack may actually reflect itself in the physical dynamics without any sign elsewhere, because it could be an insider attack, or there are components which are electromechanical, like relays and breakers and various kinds of components. And then we have the industrial automation and control, which is basically the SCADA system with various communication and computation embedded computation components. And then we have to also look at the firmware, for example, secure boot and so on. And then all the other things like software, network, and perimeter defense, and so on. at the end application software, and nowadays a lot of this functionality is going into cloud layer. And then we actually looked at the various methods that we will explore, and various disciplinary knowledge and expertise will be used for various things. For example, we have electrical engineering, power system engineering people who are actually looking into this power system, PMU-based power system monitoring, the wide area monitoring and control. On the other extreme, we have number theorists and cryptographers who are actually looking at lightweight cryptography and also breaking of various kinds of crypto and so on. Simulation and co-simulation, that often gives you a cheaper way of some proof of concept ideas, whereas laboratory emulation is the test bed that I am talking about here. So first we build this lab scale test bed. So all of you probably know that one of the biggest challenge now in most of this manufacturing system or any other critical infrastructure is the notion of IP convergence. So IP convergence means that your business network is somehow connected to your field network, the network on which your actual equipments and measurement devices and various things are there. And they are usually disconnected by, isolated by firewalls. But the problem is that once a phishing or something goes into the business network, like it happened in Sony or even in RSA it happened, then this phishing network, phishing will actually inject a malware, and that malware will actually propagate itself, find a password file, send it over to a command and control center. Some high privilege password gets hacked, and then the firewall is breached, and you go into the DMZ, and from DMZ again you do the same process, and then you go into the field network. And that's the common modus operandi of attacking the critical infrastructure. So we have to replicate this kind of a environment in order for us to actually successfully recreate the attack scenarios. And that's not the only attack scenario. I mean, there are insider attacks that don't happen through this route, but we have to have all such possible scenarios. So this is the schematics of our first SCADA testbed that we built very, very quickly after we started. And the idea there is that we want to first demonstrate that this is, in a lab scale, this is possible, and also we can successfully show the weaknesses of various industry standard equipments and industry standard devices. So this is what we built in the very first year. So on this side is our on the left side, well, my left side, your right side is actually the field system, which is basically a power system distribution panel where we have three-phase to three-phase, three-phase to single-phase, single-phase to single-phase, transformers and so on. And on this side we have relays and we have power meters, we have the protocol switches like 61850 and various standard SCADA level protocols. And then we have the data collected there, and these things actually come through various types of protocols like 61850 in some cases, in some cases 104, in some cases it's just plain Modbus, TCP, and so on. And so we have the capability now to attack from various angles. So the idea here is that an industrial automation pyramid, which basically says that at the bottom level you have the field instruments and the devices, then you have the programmable logic controllers, the RTUs, the remote terminal units, and relays and various other IEDs, and then you have the SCADA layer, which is the supervisory control layer, and then you have the other layer, which is more like interest of the business, like reporting and so on. So what we have produced here is that so the level 0 here is our PLC and various meters and GPS time sync unit and the relays and so on. Then we have the switch, and the switch basically now puts everything into the LAN environment, and then it goes into the workstations, the engineering workstations where the SCADA control and web-based control is, and that's what it translates to. So these guys are working on the actual SCADA control, supervisory control system. So what kind of attacks we have found so far, right? So these are actually industry standards. So in this case, we got all our equipments from Schneider. So first of all, the 61850 capable switch, Moxa, it's a Taiwanese company, and that switch had a privilege escalation bug. So what that means is that anybody can become the administrator of that switch and can inject data and do various things. And that way, so we have been able to do the false data injection and make wrong decisions at the SCADA level. We also found that all the standard protocols nowadays that are being used, including 61850, that are implemented by these guys, are actually unencrypted, and so we could do various kinds of man-in-the-middle attack and false data injection, DDoS attacks. We could do ARP poisoning. We could do and use that for DDoS and making the SCADA think about the configuration wrongly and so on. So we are able to show all these things, and we are reporting to the CERT of the country, but they are not doing very anything about that. But that's a different story. But now we got this money for actually building this large-scale system. So that will take about a year to actually build. This large-scale system will actually have generation, transmission, and distribution. What I showed you is only transmission, and then it will also have manufacturing automation, so process automation as well as discrete automation. So this would be like a two-zone system where we'll have solar and diesel generators on both sides, and then we'll have a power transmission with a high-tech sink, and then we'll have the loads of various kinds. There will be a home automation with a residential infrastructure. So we just started planning the new building where these things will be put in. So since I don't have a whole lot of time, I'll skip the details of each of the zones. But this is what this thing would look like. So you have this multiple control centers for the various zones in order to emulate a real utility. And then we'll have multiple substations. The substations will connect the 11 kV transmission lines. And the process automation test bed and discrete automation test bed will be connected as the load centers for both sides. So the various attacks that we have been, I already told you about the various attacks the students have been doing, and they're having a lot of fun doing this. And but it is also quite scary that these switches and these kind of devices are all over the critical infrastructure in the country. And then after November 8 demonetization, the government has been pushing the financial digital financial transactions for everybody. They have this other based transaction, which is a disaster. But all these things pushed us. We got calls from banks to actually give talks on the mobile banking security, and we didn't know anything about it at that time. So we said, you didn't invest in any kind of research in this, and now you want us to tell you how to do this and so on. So we eventually got connected to the finance ministry, and now we started looking at the financial system cyber security, which I will not talk about. But here again, we took this, the interdisciplinary approach, the various kinds of approaches versus the various layers that has to be secured, and then we actually figured out the intersections of those in this matrix, and then we trying to get our faculty of various expertise to get involved in this, who are not necessarily originally cybersecurity faculty. So, and this is the plan for us for this new FinTech cybersecurity center. It has not been funded yet, but this is what we plan to do. That would be various labs which are conglomerated for FinTech security. And then finally, I want to show the other projects, but I don't have a whole lot of time here. I have less than a minute. So we are actually looking at various things like IoT authentication with blockchains, and we have done a number of honeypots for the university. So now we have a better threat intelligence about the university system. We are working on various methods for code replacement attacks, malware analysis, very similar to what the first talk this morning we have done for P32 binaries. Of course, not with Singleton family and so on. So we have a lot of things going on, and we have multiple different collaborations. And so we have an MOU with ICRC here, and Professor Auerbach will be visiting us soon. And we have a couple of industry collaborators, including the Bombay Stock Exchange, that's the trading house. So we are doing a lot of stuff. We will have a test bed that is very unparalleled in India, and we have been partnering with top places around the country and the world. And so we are trying to make a difference in the cybersecurity posture of the country.